Pretend you are a bug on a ball. It's an inside joke. So you're a teeny tiny bug, right? You walk like this. And you're on this big ball, and it's so big that you don't really know what shape it is because you're so small. So the question is, what are the properties of something like a sphere that differentiate it from a flat surface, like the way this floor looks? Of course, we know we all live on a sphere, right? So this is, not an impractical question to ask. Of course, we all know it's a sphere. So our situation is a little bit different. It was intentional. So let's pretend, though, for a moment that we are all tiny bugs living in some kind of gigantic, universe, so to speak. But we're very small compared to the size of the universe. Maybe, just hypothetically speaking, this is the distance between us and everybody's favorite former planet, Pluto, okay? And if we wanted to know how big our actual, observable universe isn't even necessarily the actual size of the universe, it's the measurable size of the universe. And if we wanted to know how big that was, actually, I think I want to make that just a little bit smaller. There's going to be a lot of fact-checking after this. And I don't want, all those emails. So let's pretend this is the distance between Earth and Pluto. And so if you just measured that distance and you just walked out in a straight line, right, all the way to the end, and then out past the St. Constantine School gate, and then you just kept going straight until you got to Saturn, and then you went 100 million miles beyond that, then that would be the edge of our observable universe. So we live in a very, very big space. How do we know the shape of that space? It's actually still an open question in physics today. But the question really comes down to, in the beginning, what other options are there, right? So for that, we have to go back to the beginning of math, okay? And when I say the beginning of math, I don't mean like when people started counting, like 20,000 years ago, maybe. I don't mean when the Babylonians knew about trigonometry before, the Egyptians, and they were building pyramids, right? Or doing messy computations, right? Those are for physicists and for engineers, and we don't like those. I mean the beginning of mathematics that we understand today based on the axiomatic system, based on proof by deductive reasoning. I'm talking about Thales around 600 BC, Eudoxus, Theaetetus around 400 BC, and Euclid around 300 BC. Now, we don't know too much about Euclid. We only know that, he lived around 300 BC. He taught in Alexandria, and he is given credit for putting together this book called Euclid's Elements, which is the oldest textbook around today, and we still use it in our geometry classes because it's still relevant. Now, it's not perfect. Okay, we'll discuss a little bit about that today, but it is still, for all intents and purposes, very relevant to what we study in high school today. And even if you're not at the St. Constantine School and you don't study, our version of geometry, which, we very carefully go through Euclid's Elements, you're still learning the same geometry. There's no difference, right? It's not like you're learning different geometry than we're learning. I mean, you may have, some more computations. You might have to do a few other things, but we add in, we supplement. Where Euclid doesn't cover what we need to cover. But it's still the same geometry. So let's talk about the axiomatic method. What is that? Well, I have some very imperfect metaphors that I like to start my college geometry class with. And one is that math is like a building. All right, math is like a building. Okay, we start with Well, you have to have something to start with first, right? So we start with defining things. We start with definitions. Okay, so that's where we are on the screen right now. We start with our definitions. And then from that, we have different kinds of axioms. All right, so what is an axiom? Anybody know? What's an axiom? What's an axiom? You took Euclidean Geometry, right, at your other school.
In the 9th grade.
Yeah, a long time ago. What do you think?
Are the axioms the ones with... No, I'm not.
So, yes, other Euclidean Geometry teacher.
Would it be first principles or propositions that are self-evident?
Well, we would like them to be self-evident, yes. But not necessarily, right? But ideally, yes, we would like these to be self-evident. So these are sort of, I don't want to call them propositions. I don't want to call them things because that just sounds bad. All right? But they're, we'll say, statements that are unproven. Okay, we take these on assumption. And Euclid has two different kinds of these at the beginning. He has, let's see, he has his common notions, and he has his postulates. Okay, so if you go to the beginning of Book 1 in Euclid's Elements, that's what you'll find. I'm just going to scroll down. We'll come back to the definitions. There are postulates, common notions. Let's talk about the common notions because we're actually not going to talk about them that much. So the common notions in Euclid's Elements, they talk about magnitudes and comparing magnitudes and relations of sizes. All right? So when are two things equal? If one thing is equal to another, well, if one thing is equal to something and another thing is equal to that same thing, then those two things are equal. Okay, so that's like transitivity of equality. And also, if you have a whole thing and then you take a part of that thing, then the part's going to be less than the whole, things like that, right? Comparing sizes. So basic ideas, and we would like them to be self-evident. And so that's how Euclid was building his. Let's talk about the postulates. The postulates are a little bit more, I don't know, interesting. Okay? So the postulates are about what we can do with the definitions. And that's how they're different from the common notions. But they're both axioms, right? They're just sort of different kinds of axioms. And in modern geometry, I have to say, in modern geometry, we go a step further. Okay? We don't even bother with definitions sometimes. Sometimes we just say we have these primitive terms, primitive notions. Okay, not to be confused with the common notions, right? So these are, primitive notions are undefined terms. Now, why do we need terms that are undefined? Well, what happens if you start trying, did you want to answer?
Well, you just have to keep on defining like into infinity, and you can't keep on doing that.
That's right, right. And eventually your definitions, and since we don't have an infinite number of words, probably don't even have an infinite number of ideas, although maybe, it would eventually be circular, right? We have to start somewhere. Okay, and so in modern geometry, we start with these primitive notions, but it's not only because of that we have these primitive notions. It's also because we would like geometry to generalize. When I talk about a point and a line, I don't want it only to pertain to some element of, space and like something that looks like that, right? I want it to generalize to other things because that's what mathematicians like to do. We like to generalize as much as possible. What are the laws underlying reality? Okay. So let's look at a few of these definitions and common notions and see if we can understand why maybe it's best if some of these are not defined at all. Okay, let's scroll back up and we'll go back to the postulates. All right, definition 1. A point is that which has no part. Okay, so I think we all kind of understand what Euclid's trying to say. It has no part, so this is the part, right? That's the whole, that's the part. So it's something that's just indivisible. So if you divide a thing down as much as you possibly can and to the thing that it is where it can't be divided anymore, then that might be a point. All right. So, okay, we kind of understand what that might mean. But mostly just intuitively, because if you have this idea of dividing something, you have to understand size. You have to have a way of measuring maybe distance to talk about dividing something in half. So it's sort of putting the cart before the horse, right? Which is why we need these primitive terms. Let's see, a line is a breadthless length. So the same kind of thing going on. You have a line is some kind of a length of something, and it can't be, it has no width, right? Again, what is width, right? Let's see, I want to jump to a straight line, perhaps the best definition in the whole book. Okay, a straight line, this is definition 4, is a line which lies evenly with the points on itself. So, thanks Euclid, that's very helpful. Okay. So what do we think of as a straight line? These days, we don't think about a line where the points lie evenly on itself. I mean, probably not. Maybe you do. Anybody have an idea? What do you think of when you think of a straight line? A ruler, okay, sure. Usually somebody pipes up and says, oh, it's the shortest distance between 2 points, because, yeah, that's usually what we think of it as, right? Sort of, but yeah, no, a ruler, that's great. Actually, it's perfect. It's perfect. Well, I was just going to say that, well, that actually doesn't hold in all geometries, as straight lines being the shortest distance between 2 points, and so it might not be the best way to think of it. I don't want to go into what is the best way to think of it, because it's kind of beyond the scope of what we're trying to do. But I just wanted to put that out there. Say I know something that you don't know about straight lines. Okay, so Euclid's definitions, yeah, sometimes they're a little hairy here and there, and we don't quite understand what he means, which is why we start with primitive notions in pure geometry these days. And it was David Hilbert who actually came up with the present axiomatic scheme that we use, who said, well, we don't really want to define, what points and lines are. We could even say something like two beer mugs determine a table, which is like the best analogy ever, right? So we can make these relations pertain to anything. All right. Let's see. Let's talk about the postulates. So what can we do? What can we do with our definitions, the things that we have? So we're talking about the axiomatic method, okay? This basis for proof by deductive reasoning that mathematics is based on today. So we start with our primitive notions and then definitions and then our axioms. So let's talk about those axioms. What are our fundamental assumptions? Let's see. I'm going to scroll down here. Okay. Oh, that's the proposition. See, they both start with P, and I think that's really unfair. Okay, postulates. All right, so the first thing we can do, we can draw a straight line from point to point. To draw a straight line from any point to any point. Okay, so we can do that. All right, postulate number 1. We would like this to be unique, right? Euclid doesn't specifically say, oh, this is a unique line, but we would like to say that 2 points determine a line. Okay. Let's see. This also tells us something about the space in which we live. If I can always get from one point to another point, then space is connected. Now, I challenge you to think of a space that might not be connected. And if we have time, we can come back to that at the end. So to produce, this is number 2, to produce a finite straight line continuously in a straight line. Okay, so he says, well, if we can do that, all right, we can draw a line between any 2 points, well, then I can also extend it continuously in either direction. And so if I'm understanding the philosophy behind it correctly, we're not necessarily considering the lines to be infinite, but that they could go on infinitely in extent, all right? How could you have something that was actually infinite? Might be a philosophical problem. But we still understand it that way, that lines are infinite. So space might be infinite. In our notion of space, we could go this direction as far as we wanted, and that direction as far as we wanted. And we might never come to the end, but this is sort of the idea that Euclid is placing upon space right now. That's infinite in extent. Maybe it's also something called this might be a stretch, but this might be something called isotropic. Space is isotropic, which means if I look as far as I can in that direction and as far as I can in that direction, it looks the same. Okay. All right, number 3, to describe a circle with any center and any radius. So we're allowed to make circles. That's nice. All right. What is a circle?
All of the points distance are from the point of the middle.
Yeah, this is actually really interesting. We're going to talk about non-Euclidean geometries, and I'm not going to get to talk about some other kinds of geometries because I can see I'm already going long for time. But there are geometries where we can keep the same Euclidean notions, lines, points, circles, the sort of basic ideas, but we can define what we mean by distance, that is radius, differently, and then our circles will get different. So for example, since this talk is on non-Euclidean geometry, let's pretend we live in a big city and we can only travel along the streets. And so the distance from here to here is not this straight line. Okay, the distance from here to here is 1, 2, 3 blocks. Okay, so what would a circle look like in such a geometry? So the only thing that's different about this geometry from our geometry that we think of as Euclidean geometry is just what we call the metric, the way we measure distances. So if I want to draw the shape that is a circle in this geometry, it would be different. It would be, let's see, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. It's kind of an interesting exercise to see what would this circle look like, and I'll let you finish it. What do you think it's going to look like? Like a diamond, yeah. Well, yeah, like a diamond. It's a little bit different. All right. Number 4, that all right angles are equal, and this might seem like the most boring postulate of all, right? Okay, if I have so this is postulate number 4. If I have a right angle here, so a right angle, by the way, it's not 90 degrees. 90 degrees is the measure of the angle, but a right angle is the angle that's formed when you set a straight line and another straight line, and it makes these angles equal, and that's what we define as a right angle. And so it's actually a really interesting observation to make, that a right angle over here is going to be the right angle over here, because it tells us something about the space in which we live. It tells us that it's the same wherever we go. So not only do I look in this direction, I look in that direction, it looks the same, but wherever I go in the universe, things behave the same. Okay, this right angle here is also this right angle here. And so, again, this might be a stretch for all those physicists out there watching, but we might think of the universe as being homogeneous. G. I hope I'm not misspelling that. I'm a really bad speller, so I went into math. You know, I was never going to make it in the spelling community. That's how I spelled it in my notes anyway. Somebody look it up and tell me if I'm wrong. All right. But the 5th postulate is undoubtedly the best one of all. Okay, it's kind of, you know, the definition of a straight line is great, but the 5th postulate is really excellent. So, that if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than 2 right angles. I love how it's so simple, right? We can connect the dots. We can make the line longer. We can draw a circle. And this one, like a right angle here is the same as a right angle here, and all of a sudden it's 5 pages long. Okay, so what on earth does he even mean by this? Well, it's actually pretty simple if somebody else draws the picture for you and explains it. So let's do that. So I'm not being the master of the board space right here. Got 1, 2, 3, 4, and now we're back to 5 over here. Okay, so let's pretend I have 2 lines. We have what's called a transversal of those lines. All right, so T for transversal just crosses those 2 lines. And let's suppose this and this, my favorite angles are alpha and beta, so we'll use that. Let's suppose alpha plus beta is less than 2 right angles, and let's not be pedantic, all right? Just call it 180 degrees. It's okay. Okay, so let's suppose it's less than 180 degrees. All right? Then Euclid's postulate says if you have this situation, well, are the lines parallel, first of all? Just look at them. No. And which side are they going to meet on? The right or the left? The right. And that's all it says. It says they're going to meet on the side on which those angles sum to less than 2 right angles. Okay. All right. But something is different about this postulate. It sounds like something we ought to be able to prove, and we already kind of made a joke about how simple it was, and all of a sudden it got complicated. But this is what people thought for a long time. They thought that this postulate just really shouldn't be a postulate. It sounds more like a proposition. It sounds even more complicated than some of the propositions. Like the first proposition is what? Do you remember? We spent so much time doing this. It's to describe an equilateral triangle. Remember that? Yeah, remember? Yeah, we tried. No, we succeeded. We learned. It was beautiful. I won't do that proof for you, but I have it written down here. It's really easy. All right. But I wanted to mention that, these things, they're kind of empirically verifiable. They're things that we could do, that we can experience, that make sense. But how do I know that these 2 lines meet? What if the angles, like they add up to less than 2 right angles, but not by very much, right? Maybe it's like, so that looks really obvious. But what about something like, this, where the angles are they're just off by a teeny tiny bit? How do we know? Those could intersect out past the end of our, universe, right? Past Saturn or something for all we know. So how do we know that that's true? It's not something that we could just, experiment on. Okay, so people thought that they should be able to prove it. And along the way, they showed that there were many things that are actually equivalent to this, and many of them are easier to understand. And let me just give you a couple of things that are equivalent to the parallel postulate. So same as, did I give it away? Did I just say the parallel postulate? Postulate 5. We don't know it's the parallel postulate yet. All right, postulate 5. And the first thing that I have written down here is that, let's see. No, I'm not going to do Proclus's axiom. That's not very fun. Okay. Parallel lines are equidistant everywhere. Everywhere. All right, this is equivalent to this postulate. Same thing. So what that means is if you prove that parallel lines are everywhere equidistant, they're everywhere equidistant. They're not just everywhere. That would be kind of fun, no? All right, parallel lines are everywhere equidistant, right? If you can prove this, then you can prove this. Okay, so and if you can prove this, then you can prove this. Okay, so they're equivalent. Let's see, what else is interesting? All right, this is why it's called the parallel postulate. It's because it's equivalent to something called Playfair's axiom, which says if you're given a line and a point not on the line, then how many lines are parallel to this line that go through that line? What do you think? 1, right? Right, because that's Euclidean geometry. There's only one. There's only one line parallel to any given line through any given point, and that line is so that is, I'm repeating myself, that line is unique. But if there's only one, that's what it means. Okay. And also, angles in a triangle sum to what? on 180, right? This is also equivalent to the parallel postulate. If you have that, you can prove parallel. This is also called the parallel postulate because of Playfair's axiom. Okay, it's not always immediately, you don't always realize that has to do with parallel lines, but often, and in fact, in Hilbert's axioms, this one is substituted for that one because this one is just not as nice as this one. Okay. Plus, we can talk about non-Euclidean geometry easier if we talk about that one as the parallel postulate. So let's talk about Jesuit priests. 18th century, Giovanni Girolamo Saccheri. So he wanted to cleanse Euclid's elements from all ambiguities and assumptions, and I've already mentioned, that the parallel postulate was sort of the big ambiguity. There are others, but I'm not going to address those right now. So he wanted to prove the parallel postulate. This had been going on for a long time, by the way. Okay? By the 18th century, it's not like he was the only one. Many people had tried, many people had failed. And that's actually how they discovered many of these things. These things were proven to be equivalent to the parallel postulate because somebody said, oh, well, I actually proved this thing, or I actually assumed one of these and proved the parallel postulate. Well, if you assume that, you've already assumed what you wanted to prove was true, so that doesn't count. Okay. So before his death in 1733, he published something called Euclid Freed from Every Flaw. I really want to publish something like that someday. So he thought he had done it. It's really rich, but I didn't go on with this. So after we do axioms, we have theorems. We have theorems, and after we have and these are also propositions, right? And elements are called propositions. And then we have more theorems, and we have more theorems. And what happens if we remove one of these Jenga blocks, right? Because it's all about Jenga, right? Okay, it's just an excuse to play Jenga in geometry. All right, so what happens if we remove one of those? Yeah, it falls down. Or, maybe if we remove something that's not quite as big or fundamental, only part of it falls down, right? Maybe if we're lucky, we remove something that's not really that important and nothing falls down, okay? But it turns out if we remove the parallel postulate, a lot changes, okay? We might have to substitute it with a different block, and we get a different building. You see how wonderful my analogy is. Okay, so let's talk about what Saccheri did briefly. I'll try and make it brief, because it's not really as interesting as the story about Gauss, so I'm going to try and get to that as quickly as possible. So, Saccheri, 18th century. He says, okay, here's what I'm going to do. I'm going to make a quadrilateral, and I'm going to name it after myself. It's called the Saccheri quadrilateral. All right, I don't know if he named it after himself, but that's what it's called now. And so it's a quadrilateral where this side equals that side, basically. And then he connects the dots at the top, and these are right angles. Okay. Now, question to you, what's the measure of these top angles? What do you think? Yeah, they should both be 90, right? In our Euclidean universe? Yeah, that's what they are. They would be 90, but there are actually three possibilities, right? Three possibilities. So, case one, let's see, summit angles, all right, are 90 degrees, okay? And this is equivalent to Euclidean geometry, okay? This is equivalent to what we think of when we think of normal geometry. But there are other two possibilities, right? He would have to prove that. Turns out he can't prove that without assuming the parallel postulate, so he wants to do that without assuming the parallel postulate. So his idea is to do a proof by contradiction. Well, what if I assume something utterly ridiculous like case 2? The summit angles, by the way, they're the same. We can prove that without the parallel postulate. But case 2 is the summit angles are greater than 90 degrees. Okay? They're greater than 90 degrees. So what would that make the Saccheri quadrilateral look like? Well, let's redraw it down here. Okay, you got this. This is sort of 90 degrees, but the summit angles are both obtuse. So that looks weird. Could you live in a universe where that's a quadrilateral? Would you want to live in such a universe? All right, well, it turns out there's some weird things that happen if we assume that this is true. And the first thing that's really weird is that lines are finite in extent. And he thought, oh, great, I've come to a contradiction. I just erased my assumptions. But one of them was that we could extend a line indefinitely in any direction. Remember that one, right? So if lines are finite in extent, does that contradict that? Well, what if lines are something more like roundy things? Circles, okay? So they're more like, but not necessarily, right? So what if they're more like circles, right? They just kind of keep going. So you could extend them indefinitely, but they're not infinite. Okay. But he thought he'd arrived at a contradiction. So he's like, yeah, I'm halfway there to proving the parallel postulate. Because if you assume something is true and arrive at a contradiction, that thing cannot have been true. All right. What else is true? Okay. So let's think about a surface that's kind of round and on which the lines might be like circly. How about our ball, right? What we live on, like the Earth, for example. Well, it turns out the shortest, if we're going to think about lines, straight lines as being the shortest distance between 2 points, it's actually going to be like equators, okay, on the circle. And so I've put some equators on this circle for you, some straight lines. And this is kind of interesting. Here's a question for you. Are there any parallel lines if our lines on our sphere, so our space that we're working on is just the surface of the sphere, and our lines are great circles. These will, if you want to know the fancy math term for it, it's geodesic, right? Sort of the shortest distance between 2 points, but not really, okay? If there are any real mathy people watching. But yeah, for our purposes, okay, for now. So are there parallel lines? Can you think of two lines, and they have to be equators that never intersect, because that's what parallel means. They don't intersect. The answer is no. There are no parallel lines. So that's one result that would be inevitable from these summit angles, being greater than 90 degrees. All right? So we get no parallel lines. The symbol means parallel. Okay? Lines are finite. And what about triangles? I've made for you a spherical triangle here. And it's not just any spherical triangle, it's a special spherical triangle. All right. Those lines meet at 90 degrees. All right. So do those, and so do those. What's the angle sum of my triangle? All the angles are 90 degrees. Whoa, it's 270. No way. It's 270 degrees for our, and all triangles won't sum to 270 degrees. They won't. We could prove it, but I don't think we have time. So let's see. I'll say the angles in a triangle sum to more than 180 degrees. Okay. So it's really interesting, and there's a nice formula that relates the angle sum to the area of a triangle on a sphere. It's really nice. Okay, so here's some of the weird things. Like and this is interesting, because what if our universe is like this, right? What if our universe is more roundy, right, than flat? Okay, what if I keep going in a straight line and then I end up back where I started from? Who knows? You have to wait till the end to find out. Okay. All right, so what's the other option? These angles could be, oh, I ran out of room again. So case 3 is those angles, the summit angles, are acute, right? They're less than 90 degrees. Okay, so what would that look like maybe if I look like, right? This is all approximations, right? So if I had this, and then this has got to be 90. Okay, but it might look like that. Those are acute. Okay. Summit angles are acute. Huh. So that's kind of weird. Well, it turns out, I'm gonna do a spoiler alert, have this nice proof here that you guys are probably not interested in hearing anyway. But, let's skip ahead. It turns out that if I can do this, I can show that this line is actually parallel to this line. And then I can also show that there are infinitely many. If this is true, if this line is parallel to this line, then I can actually build off of this line using the properties of this quadrilateral. I can build, so this is a parallel line, and actually it's going to, maybe more accurately, it's going to curve a little bit here and here. So that's a parallel line to this line. And then I can construct another parallel line, and another, and another. I can construct infinitely many parallel lines. So that is definitely different from there being only one. There are infinitely many. Right? Through a point. Okay. So this is another kind of geometry. And what might this geometry look like? All right. Well, let's see if I can draw some kind of a picture. Does anybody you ride horses, right? You know what a saddle is. I'm going to try and draw a saddle. It's going to be really bad, but all right. Something like this. Doesn't have to be perfect. Okay, so it's kind of like a saddle, right? So let's pretend we're going to stretch a rubber band across this saddle and across it in 3 points. All right, but it's like really slippery, so it just kind of slides along the shortest possible path, right? So our straight lines formed by the shortest possible paths are going to look like this. Kind of mental exercise. There you go. That is what is called a hyperbolic triangle. All right. I didn't tell you what this kind of geometry turns out to be. It's not exactly spherical geometry being the geometry of a sphere. We would like there to be like a unique line between 2 points, and that turns out to not be the case on the sphere. But if we sort of look at the hemisphere, then maybe we can, and sort of identify certain points, then that would be a geometry where lines were determined by 2 points, and this is called elliptic geometry. Okay, so these are the properties that hold an elliptic geometry. But most especially the angles of a triangle sum to more than 180 degrees. Now this one turns out to be something, it's a non-Euclidean geometry, right? You start out with the first 4 postulates and discard the 5th, right? And you replace it with something else. And that, that 5th postulate might be the sum of the summit angles, not the sum, but the summit angles of the Saccari quadrilateral are acute, okay? That might be your 5th postulate, although I don't like that one. It'd be better to say that there are infinitely many parallel lines to a given line through any point, not on the line. Okay, because that sounds just like Playfair's axiom, which has the word parallel in it when you say it out. So this one obviously relates to that one in some way. Okay, so this is going to turn out to be something called hyperbolic geometry. Hyperbolic. Okay. It's called hyperbolic geometry because one of the models is on the surface of a hyperboloid. Now, your lines, if you think about lines being on the sphere, they were equators, right? Well, another mathier way to say that is, well, they're formed by the intersection of planes going through the center. okay, and just the intersection of the sphere with the plane going through the center. So this is a hyperboloid, and we just want to look at the top, but my lines in this geometry on this surface are going to be planes that go through the origin, which here I removed it, but you know where it is. And it's going to be the intersection of the hyperboloid with the planes through the origin. All right, so I'm going to move this around so you can see it. Can you see the hyperbolic triangle? It's kind of hard to see. Right here. See the hyperbolic triangle? Yeah. It's easier to see from the top, I know. There we go. Yeah. So super cool. I can spin this thing. That's cool. Okay. Hyperbolic geometry. One model is on a hyperboloid. All right. So Sakari, you know, he did his analysis. He came up with different theorems, one of them being that this is a triangle and the angle sum is less than 180 degrees. Okay? And in the end, he really couldn't find a contradiction. So here's his contradiction. It's really rich. Just like right before he died. He says, the hypothesis of the acute angle, that's this assumption, right, is absolutely false because it is repugnant to the nature of a straight line. I love that. I was watching other professors give talks in preparation, trying to think of how this should go. And one of them described this as proof by disgust, and I really like that. All right. So, Sakari, he thought he'd arrived at a contradiction, so he didn't really develop these ideas very much. But let's jump ahead to the 19th century. And we have a young, budding mathematician, Janos Bolyai, or Janos, I'm sure I'm pronouncing it wrong. His father was a mathematician, okay? And his father said, absolutely, under no circumstances, try to go down the rabbit hole of trying to disprove the fifth postulate. It will only bring you sorrow. And do you think he listened? No, of course not, because kids never listen. So he developed hyperbolic geometry to a significant extent. He was quite intelligent. But he was a bit dramatic. And so he's credited with saying, out of nothing I have created a whole new world. Right? That's one of his famous quotes. All right. But his father was friends. Let me see. I have a picture of Janos here. Nope, that's not it. There we go. Let's see. Non-Euclidean geometry. There we go. There he is. Look at that young whippersnapper. All right. So he came up with hyperbolic geometry and developed it to a significant extent. His father was friends with a mathematician named Gauss, who is perhaps the greatest mathematician of all time. But he's kind of grumpy, okay? So he's, you know, lovable because he's kind of unlovable. And so his father sent Gauss what young Janos has been working on, and he thought Gauss would be really impressed, and he could, tutor him, he could help him, give him exposure. But Gauss was kind of grumpy, like I said. All right, I wanted to share one example of that. So one example was, he's credited, I don't know if this is a true story or not, but he's credited with when his second wife was on her deathbed. He was so involved in his work that when they sent for him, because it was her last moments, he said, can't she wait? So I love that. But he didn't publish very much because he really didn't like controversy, and I think he just didn't like criticism. And so he didn't want to publish anything that was not just absolutely perfect and told the whole story of what it is he wanted to say mathematically. So he didn't publish a lot. So here was his response to Bolyai's father. He said, to praise it would be to praise myself. For the entire content of the work coincided almost exactly with my own meditations, which have occupied my mind for the past 30 to 35 years. So he already knew about that before it was cool. I think I also stole that from another professor. Okay. But anyway, in my mind, Gauss, oh, by the way, I have a picture of Gauss. Let's see if it's coming up next. There he is. He looks like Scrooge to me, and this is how I think of him, right? Yeah, it is the hat, but also the nose and the mouth and the personality. All right. So this sort of upset Bolyai to a significant extent. He stopped doing math as far as we know and sort of died in ill health and obscurity later in life. All right. By the way, another young man, intelligent, also separately came up with hyperbolic geometry on his own by saying, well, what if the parallel postulate is not true, and he developed this all by himself. Oh, angles in a triangle sum to less than 180 degrees and a bunch of other interesting things that we don't have time for. So this was Nikolai Lobachevsky, and the only reason he wasn't given credit at the time is because he published it in Russian. So nobody really knew about that. Okay, elliptical geometry, which we've already discussed, that Sir Carey had discovered, was developed further by Riemann, and then both of these systems, and I think this is really interesting, both of these systems were not proven to be self-consistent until Eugenio Beltrami did it. He finally provided a proof in the 19th century. So what does it mean for a system to be entirely consistent or self-consistent? Well, it's definitely doesn't have any flaws in it, or at least if it does have a flaw, so if there was something wrong with hyperbolic geometry, it's every bit as consistent as Euclidean geometry. So if there's something wrong with hyperbolic geometry, then there's also something wrong with Euclidean geometry. And so that's what it means for the system to be consistent. Both elliptic geometry and hyperbolic geometry were proven to be just as consistent as Euclidean geometry. So how do we know the shape of space? We might live in a non-Euclidean universe where straight lines do not behave as we think they should. What characteristics distinguish a curved space from a flat space? Well, one idea is measure the angles of triangles, right? Okay. Gauss actually did this according to some accounts, right? He lit fires on some mountaintops and then reflected some light and measured the angles, and it turns out that it was really close to 180. So that's a big letdown, right? And actually, as far as we can tell, I'm talking about three-dimensional space right now. As far as we can tell, yeah, the universe kind of is flat, right? But, you know, there's some margin of error. So it's either it's flat, it's Euclidean, or if it's curved in some way, then not very much so, as far as we can tell. But then again, what are we? We're bugs, right? Bugs on the surface of the universe. But I think what's more interesting, and this is also what I know the least about, is that the question of what is the shape of four-dimensional space-time has a non-Euclidean answer. It's this one, it's hyperbolic geometry. The current model, based on Einstein's general theory of relativity, is a hyperbolic geometric model. So what does space-time mean? Well, we're wrapping up three-dimensional space and time into one, and that's about as much as I'm going to go into that at this point. But it's a really interesting thing to think about, and so I hope that many of you will go into physics and come back and teach me all about it, because it sounds really interesting. But the point being that maybe reality is more like hyperbolic geometry than it is about Euclidean geometry. And so if we think about reality, why shouldn't that include time? All right. So, we have time for like 3 minutes, right? How far am I supposed to go? Okay. 3 minutes. All right. So, do we want a joke or a deep philosophical quote? What do we want? All right. Okay. Well, now I have to do both. All right, so this is a really bad joke, but I did promise some of my students I would tell one, and so, I mean, the whole thing has been a really great joke, right? But so, it starts like this. Euclid, Gauss, and Bolyai walk into a bar. It's a juice bar because we're minors, some of us. And we'll let Lobachevsky be the bartender because he's got to play a role somehow. So Lobachevsky says, what do you have, sir? to Euclid because, he's really old. And Euclid says, I'll have a drink of wheatgrass where the drops lie evenly among themselves in a vertical fashion. And Lobachevsky just looks at him and says, one shot of wheatgrass straight up. All right. It's original Neacsu right here. Bolyai turns to Lobachevsky and says, I have invented a strange new drink. Infinitely many shots of wheatgrass passing through a single glass. Impossible, says Euclid. And Lobachevsky mutters something under his breath, but it's in Russian, so nobody understands. And Gauss grabs Bolyai's drink and says, this was mine from 30 years ago. All right. There's more, but I'm pretty sure it's bad, so I'm not going to say it. All right. All right, so I want to close on a very deep philosophical quote. So Henri Poincaré is sort of given credit for a model that Eugenio Beltrami made of hyperbolic geometry. It involves a disk, so let's shrink all of space down into a single disk. This is already a great idea. Okay, and then let's model the straight lines as being circles that run perpendicular to the outer rim. And if you've ever seen some of M.C. Escher's sketches, that's what they're based on. These ones, they're called circle limit. Okay, this is hyperbolic space right here, a model. Okay, anyway, Poincaré gets the credit even though he just rediscovered it, right? Kind of like I rediscovered some of the jokes in my lecture today. But he had some deep things to say about geometry. And he says, the axioms of geometry are only definitions in disguise. What then are we to think of the question, is Euclidean geometry true? It has no meaning. We might as well ask if the metric system is true and if the old weights and measures are false. One geometry cannot be more true than another. It can only be more convenient. All right. Thank you for coming.